Okay, let's get started. I've been having fun with memes on the announcement slide, so or at a minimum, movie references and whatnot. Given the weather today, this seems appropriate. I know at least some of you get the reference. Okay, a couple quick heads ups. Attendance is up to date. I graded homework 2.1 over the weekend. That everybody seems to do pretty well with that. What about 2.2? I know that one was a little different because it was all based on a pre-recorded lecture that I wasn't here for. Everybody okay with that? Because I wanted to make sure that was clear. If anybody had any questions on that, let me know. If there was something about it that was confusing, we can discuss that either now or after class and whatnot. Homework 2.2 good? Okay, good. Homework 2.3 is going to be assigned today, due Wednesday. Again, I think 2.3 is going to be pretty short. 2.4 is probably going to be a little longer because so these past few assignments have been little snippets, and 2.4 is sort of putting it all together. One other note I put in the attendance survey today. And I think I mentioned this in my last email. It is just so darn convenient to send announcements to the class on Teams as opposed to sending an email. It's just faster. And I want to make sure, especially in the middle of potential inclement weather issues, that you're informed. Like one of the things I don't want to have happen is if I want to keep on rolling with the lecture schedule, but I don't want anybody to come out in the morning, especially if the university closes and whatnot, is I want to be able to get the word out pretty quickly. So I think from here on out, I'm just going to be making class announcements on Teams and whatnot, but I did want to make sure that everybody can access it. So I put a note or a question on the attendance just to make sure everybody can access it. If anybody has any issues about accessing Teams and whatnot, we can talk about that later. The only other thing I would mention is Dr. Zatar, who is teaching mechanics of deformable bodies, is still looking for a TA for the class to grade some homeworks. If anybody is interested, let me know. If you're in this class, that means you had deformables and passed it. So anybody that's interested, come see me after class and I'll get you set up with them. Okay, any questions? Okay. So I've got some stuff here on the whiteboard. I'm going to explain that here in a second, just to sort of set the stage for where we are now. Oh, that's the wrong lecture. I need to go to lecture 6. To go to where we are now in the class. Let's see. Okay. All right. So I've got some stuff here on the board. Let me sort of explain what's going on here. So I told you that really the basis of everything that we would be doing this semester sort of hinges on this equation right up here, this inequality, that the resistances need to be greater than or equal to the loads. Now, on the load side, we already sort of dealt with that already because, this fancy notation is really just saying that we have nominal loads like dead loads, live loads, snow loads, wind loads, etc., and we plug those into our statistically calibrated load combos, like 1.4 dead, 1.2 dead, plus 1.6 live, etc. And from these, we take the maximum, right? That's going to be our worst case loading situation. Everybody with me so far? Okay. Now, what about on the resistances? Well, the resistances are going to be a function of the various limit states that we need to investigate for a given member, okay? Now, we've already seen some of these, and they're going to show up here in the slides here in a second, but let's just sort of formalize these. So, for a tension member, one of the limit states that we need to assess is the limit state of yielding in the gross section. Now, in order to compute that capacity, so we call this phi PN. So just so you're aware, we know phi RN is sort of your general term for resistance, but we'll have like a phi PN for axial loads, a phi MN for moments, and what have you. So don't get too marred up on that. But we have our factored resistance equals our yield stress times our gross area times our resistance factor. And for yielding, it's 0.90. So I just want to take a look at this equation real quick and ask, can we do this? If I gave you a problem and asked you to compute the factored resistance according to gross section yielding, could you do it? Well, do we all know how to compute gross area? I would say by now we should be able to. What about yield stress? If I gave you A572 grade 50 steel, can you look up the yield stress? Hopefully by now you can. So this limit state is pretty handleable right now, okay? Now, what about net section fracture, okay? Well, net section fracture says that our phi PN equals, okay, we need a resistance factor, so it's 0.9 up here, down here it's 0.75. We need a stress. Well, if it's Fy up here, it's Fu down here, okay? And what about the area? Well, the spec says that the area is the effective net area, but we saw a little bit ago that we could replace that with just the net area times U, okay? So let's take a look at this limit state. Can we compute, well, we know what 0.75 is. We can look up the tensile stress. What about net area? I mean, I think we've sort of beat net area into the ground, right? I mean, that's what we've been doing for the past couple days. So is there anything that we have yet to talk about? That. We haven't talked about that, right? That's what's left, is U. So once we discuss this, we'll be able to start analyzing tension members. And if we know how to analyze tension members, we can start designing them. So we can start to see sort of the big picture of where we're going over the next couple days. Now there is a third limit state. The third limit state is block shear rupture. We're going to talk about that later. We will talk about it, but we'll handle that a little later. Now another aspect I'll mention is, let's just sort of make sure we're all understanding. Over here, when we're looking at loads, we have a series of load combinations, and for the purposes of design, we take the maximum. If we're assessing a tension member's capacity and we have multiple different limit states, which one is going to control our design? If over here it's the maximum, what about over here? It's the minimum, yeah. So the idea is that here's the idea. So let me write this down. From these, take the minimum. So the idea is that if I compute that the gross section limit state is 300 kips and the net section fracture limit state is 400 kips, the idea is, imagine taking that tension member and start applying load. Which is going to happen first? Which number are you going to hit first as you increase the load? You're going to hit 300 before you hit 400, right? So that's going to be the point at which the member fails, whichever number is lowest. Does that make sense? Does that concept kind of make sense? And don't worry, we're gonna dive into this with much more detail a little bit later. And again, as long as your factored resistances are greater than your factored loads, the member is safe. Okay. So yeah, so we're looking at tension members right now. We have the gross section and we have the net section. Remember, the gross section is the main body of the member. And this idea of the main body being away from the connection is going to be kind of important here in a second. But just recognize that the gross section is away from the connection. Okay? Now, the net section is there through the connection. And when I first showed you this graphic, I said I was going to sort of be fast and loose with the lead line. But now, hopefully, you understand what the lead line is. So if you're standing here on the member and you shine a flashlight, the lead line is the bolts that are directly seeing light, that are not going to be hidden behind the shadow of the bolts behind them. Okay. And so here's what I've got up here. This right here is what I've got written on the board. The idea is that we've got the tensile strength, we've got yielding in the gross section, fracture in the net section. And the spec says that the fracture in the net section is the ultimate tensile stress times AE, but AE is just the net area times U. So this is just me collapsing everything into to one series of expressions. And so here's what I got. And again, if you look at this, this slide and you look at these terms, every single thing here on this slide, we've either discussed how to look up or how to compute, except shear lag. That's the one thing we haven't, for one, we haven't really even discussed it. We haven't really discussed how to compute the shear lag factor, okay? Fortunately, the math the formulas are pretty easy. The theory and what's going on is kind of tricky, but the way that we handle it is pretty straightforward. Okay, and again, we're going to add a limit state to this later. The equation is a little messier, but it's not hard to do. Okay. Okay, so let's talk about shear lag, and specifically what these shear lag factors are. These U values are what are called shear lag factors. But in order to discuss shear lag factors, we need to understand what shear lag is. Okay. Now, let me sort of take a step back and talk a little bit about Engineering 216, about mechanics of deformable bodies. This was the section that Dr. Zatar is teaching that he was looking for a TA. In mechanics of deformable bodies, and I want to be clear, we engineers use the principles in that class just as we use the principles in fluid mechanics and what have you for the vast majority of what we design. But the thing is, mechanics of deformable bodies, just what you learn in that class, will only get you so far, because sometimes we engineers deal with situations that are just tricky, that are just complicated. Okay, and we see it in all sorts of areas of engineering. Like, for example, you folks in one of Dr. Waite's classes in hydraulics know that you have these beautiful fluid mechanics expressions that'll work for characterizing flow, and then there's this thing called friction and open channel flow, and suddenly you break out a lot of these empirical expressions to handle the head losses and things like that. Well, in mechanics, we have similar situations where sigma equals P over A is great, okay? But sigma equals P over A has some assumptions like prismatic members, that the load is applied evenly, and so on and so forth. Now, that isn't always the case, and a very clear example of where we get some really weird stresses are in steel design. Particularly when you have a member and you drill some holes through it and you yank on that member, the stresses get weird. Okay, they just get very, very irregular. Okay. Now, how many of you have heard of finite element analysis? How many of you have heard of that before? Hopefully, some of you have. If not, finite element analysis is what we did last semester with Masthand, just sort of on steroids. Okay. Masthand, if you recall, was a software that would numerically analyze structures. It's analyzing very simple structures. We can use finite element analysis to analyze really, really complicated structures under all sorts of different stress conditions and material behaviors and what have you. Okay? So the reason I mentioned finite element analysis is if you really want an accurate picture of what's going on with stresses and deformations, and you don't think that mechanics of materials is going to get you all the way there, that's where finite element analysis comes into play. To be blunt, most civil engineers in practice usually try and avoid doing finite element analysis because it is complicated, it takes time, and time is money. Okay, but it's not to say it isn't used. So, like a good example of where you'll see finite elements or matrix analysis work, let's say in bridges, are whenever you have bridges that are really curved or really skewed, you'll probably find engineers breaking out the FEA in order to accurately get moments and shears. I mean, there are some tips and there are some shortcuts that you can do that by hand, but nowadays with computers and whatnot, you'll find engineers using that. This was from a research project that was done at WVU a few years ago, and it was looking at this phenomenon of shear lag in members with connection eccentricity. That part doesn't really matter for the purposes of what we're discussing here. What I want you to sort of pay attention to is what's going on in these rainbow colored plots. So this is a stress contour. And so what's happening is we're taking this tension member. We can see that the tension member has 3 bolts here or 4 bolts here. And we're taking this tension member and we're yanking on it. Okay? And what we're seeing is what happens as the stresses propagate throughout the member. Okay? Now out here, this is the gross section. This is the gross section. And to keep this basic, the colors are all sort of the same out here. They're all yellow, right? And so what this sort of indicates is that the stresses are very uniform out in this area right here. They're very, very even, uniform. You get the same stress here as you do here, as you do here, as you do here. They're all pretty much the same, okay? But that's not happening right here. Right here, the stresses are all over the place. Like, so for example, the red areas might be areas of high stress. The blue areas might be areas of low stress. So you can see up here, like up here and up here, the member's hardly seeing any load, but as you start yanking on it, you see a lot of stress right here and what have you. These stress discontinuities and these non-uniform stress distributions are something we have to deal with. We don't get to ignore them, okay? The other thing that's worth mentioning is that they are occurring at the net section. They are not occurring on the gross section. So we have 0.9 FY AG, and we have 0.75 FU AN, but we throw a shear lag factor on this. We don't throw it on the gross section because it's not happening here. It's happening here, okay? Does that make sense? So what is this U value for? This U value is to account for the fact that stresses are not uniform there at the connection, okay? So typically what happens in most steel design, like common steel design connection scenarios, let's consider this. This is a W section right here. This is a W section, and it is connected via the flanges. So the bolts are going through the flange, but they're not going through the web. And that is very common. It's very common that you don't connect all of the cross-sectional components, that you only connect some of them. So in other words, we're connecting the flanges, but not the web, okay? Then what you do is you take this member and you apply load, okay? So as you apply load, what's happening is the flanges are gonna see that stress first, okay? And then it's gonna take some time for that stress to propagate throughout the member. Now here in the gross section, the member's seeing pretty much uniform stress throughout the cross section, but that's probably not happening right here at the net section. Right here at the net section, the flanges are seeing a lot more stress and load than the web is, okay? So the question then is, at the net section, how much of this area is effective in resisting load? So what we'll do is we'll take this net area and reduce it a bit, to account for the fact that some of the section is seeing load, some of it isn't. So that part of the cross section that isn't seeing load is sort of lagging behind. Okay, so some of it's being loaded, some of it isn't. And so inside the member, you have sort of this shear effect happening. That's what shear lag is. The idea is that some of the member is seeing load and some of it isn't. Okay, does that make sense? Does everybody kind of get that idea? Okay. Now here's the thing. In order to accurately capture shear lag, you know, with some scientific specificity, we need some heavy-handed computational tools. But we're not going to do this for every single member. We need a simple way of handling this. That's where empirical expressions come into play. So there is a difference between a mechanistic expression and an empirical expression. And so I'm sort of breaking these into two big chunks, but we engineers tend to use both mechanistic expressions and empirical expressions. Mechanistic expressions are things where you can break up in a physics book, break up in a calculus book, derive some equations, and boom, here's an answer. You can actually take the expression and sort of tie it back to a fundamental theory of physics or math or what have you, that it's grounded on some theoretical basis. That is a mechanistic expression. An empirical expression is take a bunch of tension members, go down to the lab, yank on them and break them, collect a bunch of data, and curve fit an expression that best fits that data as closely as possible. Sure, there are probably some theoretical underpinnings to that behavior, or to that data, but really the data is is more reflective of trying to best, or that equation is trying to best fit the data as opposed to rely on some theory. And we use that in all aspects of engineering as well. So that's what shear lag factors are for. These are sort of empirical expressions. Now, you can find these in the manual. They are on page 16.1-34, okay? I think everybody ought to turn to that. One thing I'll mention is right here, if you look at my manual, I have myself a little tab here, because what I can do is my manual is shut, boom, I found it, okay? This is a tabbable page in the manual, if there ever was one. A lot of students ask me, what pages should I bookmark in the manual? This is probably one of them, okay? This is the section of the shear lag factors in the spec. If you remember, I posted the specification to Blackboard, okay? So here's the specification. This is what's in that back section of the manual. So if you go to Chapter D, here's Chapter D, go down a couple pages, and here we go. Here's that section. Let me make this a little bigger. Here, I'll close the bookmark page, make it a little bigger. So this is the table that will illustrate shear lag factors for tension members of various different connection scenarios. So we have a series of different cases. We have case 1, case 2, case 3, all the way down to like case 8 on the next page. What I'll tell you is that it is possible that for a given connection, multiple cases can apply. So there are some general cases at the very beginning which are trying to be as widely applicable as possible, and those are really cases 1 and 2. Cases 3 through 8 are a little bit more specific, talking about very specific connection scenarios. We've got pipes, we've got welded sections, we've got W shapes and what have you in these various connections. But cases 1 and 2 are the ones that are sort of generically applicable to all members. Okay, so let's talk about cases 1 and 2. Okay, so I'm going to read these cases out, and I'm sort of shortening some of the text a little bit here on the slide, but the point is salient enough. So the difference between case 1 and case 2 is the following. So case 1 says if the load is transmitted to all of the cross-sectional elements by fasteners or welds. Case 2 says if the load is transmitted to some of the cross-sectional elements by fasteners or welds. Okay? And it also says exceptions for HSS, and there are some exceptions and what have you. So just to sort of illustrate what I'm talking about here, okay, what I'm saying is let's consider an I shape. And let's consider an I shape over here, same thing. So an I shape for case 1, okay, it says, what does case 1 says? If the load is transmitted to all the cross-sectional elements by fasteners or welds, then U is taken to be 1.0. So what it's saying is that for case 1 to be applicable, we have to have bolts through all cross-sectional elements, the flanges and the web, okay? And so what case 1 is saying to the engineer is, yes, stresses are going to be discontinuous. They're going to be weird. But as you apply load, because all of the elements are connected, there isn't enough of that lag phenomenon present so that you need to reduce the net area. In other words, even though the stresses are weird, we can assume that the entire cross-section will reach FU. So in other words, for case 1, U is 1. Okay, but what about case 2? Case 2 says if the load is transmitted to some of the cross-sectional elements. And this would be a case 2. Case 2 would be maybe the flanges, but not the web. So this would be case 1. This would be case 2. Okay? I'm sure some of you are thinking, well, you got all, some, what about none? Well, if none of the elements are connected, then there's no tension member. You got to have some connection. Okay. So case 1 and case 2 are the ones that pretty much apply to every case, either or the other. And the formula for case 2 is 1 minus x bar over L. Does everybody see that in the table? Okay. Now I'm writing it a little differently here on the slide. I'm saying x bar sub CON, L sub CON. And there's a reason for that. The reason for that is there is a difference between connection eccentricity and just what x bar is in the manual. Okay, so for example, if you're doing W sections connected by the flanges, the value for this is actually a y bar value. So I want to, like, what you as the engineer have to do is figure out what x bar is. It's not an automatic just look up x bar for that shape. In most cases it is, but we'll take a look at that here in a second. All right. Now, case 2 is really broadly applicable, so we need to take some time and discuss that. In order to understand what these terms are, we're going to take them one at a time. Let's start off with connection eccentricity. This is this x bar term. Connection eccentricity is defined as the distance from the connected face to the centroid. Okay? So if you have an angle, let's say you're looking at this angle right here, the centroid of an angle, y'all remember what the centroid is, right? That's that geometric center of gravity for that cross section. The center of gravity, or the centroid for an angle, is about right here, okay? Now, if we look at this angle, okay, this angle, we've got this leg is not bolted, this leg is, okay? So the connected face what is this going to be connected to? It's going to be connected to some plate right here, right? There's going to be a plate right here that it's connected to. Does that make sense? So this is the connected face. This is the centroid axis. And that term right there is x bar. Okay? So what you need to do is you need to be able to open up table 1-7 or 1-5 or what have you. Remember remember this? Remember that whenever you look up sections, like right here, here's an angle. There's that little schematic up top that tells you what the dimensions are, right? You need to be able to look up the appropriate term and say, okay, for this member, that's x bar, or for that tension member, that's y bar. You need to be able to look up the appropriate dimension and use that accurately. Okay? Now, for a channel, for example, it is in fact just x bar. So you go from connected face to where the centroid is, and it's x bar. There is a specific case where it's y bar, but I'm going to show you that here in a second. Okay? Does everybody get the idea so far? Okay. Now, I want to be clear about this term right here. Okay? I want everybody to open up the angle table because I want to show you something. Okay? So if you open up table 1-7 for the angles, I want you to notice something. If you look at the, it can be angles, it can be channels, what have you. Angles are sort of the easiest place to find it. So I'm on page 1-45, okay? Doesn't matter, any one of those tables. If you look at, so we've got the area, see how there's like an axis XX and an axis YY, does everybody see that? Okay, does everybody see how, so like if we look at axis XX, there is an I value, an S value, an R value. Then there's like a Y bar, and then later on there's a YP. Does everybody see that? See how there's a Y bar and a YP? I want to see if everybody's able to see that. For now, ignore the YP, okay? Don't just ignore it, okay? And I'll explain why. We are going to use those or know what those are later, okay? I don't want to get too far down the rabbit hole for what YP is, but suffice it to say that Y bar is where the centroid is. But YP is a specific location on the cross-section related to bending, okay? And we're not talking about bending, we're talking about tension members. We're talking about yanking on members. So for now, ignore that. Don't use the XP or the YP for anything. Don't worry, we will explain what they are later. Okay, now, there is a special case which happens very commonly for tension members, and that is whenever you have a W section connected by the flanges. Whenever you have this case, what's going on is that the idea is that as you yank on this member, the idea is that half the load goes up top and half the load goes to the bottom. So what we do is we sort of, if we want to find a connection eccentricity, what we do is we say, okay, here's the W section. Let's turn it into an equivalent WT, okay? And then for that WT, we look up its centroid, and its centroid is Y bar from the connected face to the centroid. Now, how do we do an equivalent WT? Well, remember, so let's say we have a W12 by 30. Remember, what does the 12 mean? The 12 is about how deep it is. What does the 30 mean? About how heavy it is. So a W12 by 30 split in half is a WT 6 by 15. Half is deep and half is heavy. So if we ever have a W section connected via the flanges and we need the connection eccentricity, if we have a W12 by 30, we look at Y bar for a WT 6 by 15, and that's the connection eccentricity that we use. Does that make sense?
Just for W shapes?
Just for W shapes connected via the flanges. It's a special case. It's the only one that we consider this for. With other cross sections, you can usually look up the centroid directly, but not for this. Okay. Does that make sense? Don't worry, we're going to have practice with this, so don't think we're. I'm just going to say, oh, you got it. No, we'll practice this stuff. Sound good? Okay. The connection length is pretty easy. The connection length is just the out-to-out distance from center of bolt to center of bolt along the length. So however far the distance from the out-to-out distances between the first and last bolt hole, that's the connection length. That part's pretty easy. So with that, I don't want to harp on that too long because I got another topic I want to talk about, which is slenderness. Okay. Does anybody have any questions on this? Don't worry, we're going to practice this stuff. Don't worry. Okay. Let's talk about slenderness. Okay, now if you go back to chapter D and go to the very first page on chapter D, it's kind of funny. So we are talking about slenderness limitations, and if you look at section D.1, it says there is no maximum slenderness limit for tension members. And you go, well, Dr. Mike, why are you talking about this? Okay, let's dig into this a little further. Okay, so first off, what we are talking about right now is our first taste of a service limit state. Remember, everything up here is a strength limit state. These are strength limit states. These are the ones that if we violate these, we're causing danger to the public. Whereas violating these are not going to cause danger to the public, but they are going to inhibit the structure's day-to-day performance. Now, what the spec is saying here is it says there is no maximum slenderness limit. But let's dig further. If we read the user's note, what it says is, for members designed on the basis of tension, the slenderness ratio of the member as fabricated preferably should not exceed 300. Now it also says this limit does not apply to rods. We'll talk about that later, but for now it says that the slenderness ratio should not exceed 300. Now before we talk about what slenderness is, let's talk about why. Okay, when we apply slenderness limits for tension members, we do it for very specific reasons. Okay, if you've ever been to a steel fabrication outfit, like if you ever get a chance to go to Huntington Steel and do a tour of their place, you ought to take a chance and do it. If you've ever seen steel during fabrication, like once it's fabricated and you're lifting it about its strong axis, it's incredibly stiff. But about its weak axis or lifting a plate by itself, steel looks like it's got about as much stiffness as a wet piece of spaghetti. Because as steel gets really, really long and really thin, it can get kind of flimsy as you're lifting it. So maintaining some sort of slenderness limit on tension members can make tension members a lot easier to handle during erection of the structure, during shipping of the structure. You can ensure that the members don't have excessive sag under their own weight, excessive deflection under their own weight, vibrations, etc. So even though the limit says, or the spec says you can get by without applying one, most engineers will apply a cap of a slenderness being less than or equal to 300 for these reasons. And we are going to apply that limit in here as well. Again, this isn't about strength, this is about day-to-day performance. Now, what is slenderness? Okay, so what is slenderness? All right, so I want to go back to mechanics and materials, and I want to talk about the moment of inertia. Okay, now do you all remember in mechanics and materials what the moment of inertia is? So the moment of inertia will tell you how stiff it is. Everybody's being drawn to my little Slender Man poster. I'm like, why is there something out here? You'll see. All right, so the moment of inertia will tell you how stiff an element is under bending. So I brought here my my little rubber I-beam, or what I like to call my student behavior corrective device. That's a joke, not very funny one. All right, so if I take this and I try and bend it, it's a lot harder to bend like this than if I take it and turn it 90 degrees, it's a lot easier, okay? And the reason why is because the moment of inertia about this axis of bending is higher, okay? There's a larger moment of inertia here than it is here. And you can see this in the spec. Like if you turn to the W shapes, just any W shape, and look at the I values about the x-axis are always bigger than the I values about the y-axis, okay? We have a name for that. We call it the strong axis versus the weak axis. So it's like, how many of you have ever, like, you know, you have a house and there's like a deck in the backyard, like a deck or a porch or something like that, and you look at the floor beams under the deck. The floor beams are faced up like this. They're not like that, right? Because if you want the floor beams to be stiff, you face them upright, right? If they're like this, they're just going to bow as soon as you stand on them, right? So you face them upright so that they're stiff. The reason is because those wooden planks have a higher moment of inertia if they're faced like that versus if they're faced like this. Make sense? Now, here's the problem with the moment of inertia. The moment of inertia has units of inches to the fourth. It's kind of a weird term because what you're doing is you're taking an area times a distance squared. So moments of inertia have a really large, a really odd unit system. So if I want to simplify a moment of inertia, an easy way of doing it is take inches to the fourth, right? So inches to the fourth, divide it by inches squared, which is the area, and take the square root. What units is that going to come in? That's going to be inches, right? So a radius of gyration is just taking the moment of inertia and resolving it to units of inches. It's just a way of normalizing the moment of inertia. So R, like I, is just a way of expressing how stiff an element is. And so like this I-beam, it's stiffer this way than it is this way, okay? So R is a measure of its stiffness. Well, if I take the member length and I divide it by the radius of gyration, I get slenderness. That's what slenderness is. So the slenderness of a member is defined as L over R. It's a really nice mathematical definition because L over R is unitless. Does that make sense? Now, just to give you some mental construct as to what slenderness values are, if you were to compute the slenderness of a Campbell's soup can, it would be about 6. Okay, that's about how the math works out. Versus like on the flip side, if you were to take these a single spaghetti noodle and compute the slenderness, it's about 500. Okay, so that gives you kind of an idea. I'm thinking something like this probably has a slenderness of about, I don't know, like 60. I don't know. I could actually probably compute it and look it up, but I might do that one day just to see. That's about how slenderness is. And I think you could probably imagine if this element, so how long is this, what, 2.5 feet? Imagine if this was like 20 feet long. It would just kind of be hard to lift, hard to handle, right? So we put this slenderness limit on there for construction purposes. And as for Slender Man, I have no idea how slender he is. So, okay. Now, whenever you're computing slenderness, make sure that you're paying attention to units. The radius of gyration, when you look it up, is in inches, okay? But if I'm talking about how long a member is, I'm probably talking about how long that member is in feet. Like I have a member that's 20 feet long, and its radius of gyration, bless you, is 2.6 inches. There's a units problem. So typically, your member length needs to be converted to inches in order to get a dimensionless quantity, okay? Now, the only other thing I'll mention is that for the radius of gyration, whenever you have a section that is symmetric, like a W shape, use the minimum of Rx and Ry. If you have an angle, you're going to use the minimum radius of gyration altogether. And if you look at angles, there's actually an RZ term. That's what RZ is. It is the minimum radius of gyration because an angle does not have symmetry, except if it has equal legs. So. Oh, and one other thing. This is just a check for serviceability purposes. When we go to columns and beams, we're going to think of slenderness in an entirely different way because slenderness is going to affect capacity in a real big way when we start talking about columns. All right, sound good? Okay. So I want to go through a couple of examples on how to compute shear lag and slenderness quantities. Again, I think you're going to find this is very easy, okay? So I've got two shapes here, and I want to determine the shear lag values, or the U values for each of these shapes. I'm also asking another question about the channel. Does the channel meet suggested slenderness limits if it is 15 feet long? Okay, so we'll see what that means here in a second. Okay, let's take a look at this. Okay, so we have a C10 by 30. Okay, so let's start off with the shear lag values. Okay, here, let me make this bigger. And let me get my keyboard out of the way so I can write a little bit more easily. Okay. Okay. So the shear lag factor, okay? So the first thing that we're going to do is we're going to go to that table in the spec. We're going to go to 16.1-34. We're going to go to our shear lag table. And we're going to ask ourselves, how many cases apply. Note that for a given tension member, it's possible that multiple cases can apply. Now, the first question I usually like to ask myself is whether or not we are dealing with a case 1 scenario or a case 2 scenario. So you tell me, for this tension member, are we dealing with case 1 or are we dealing with case 2? Case 2. Why did you say case 2? Exactly. We've got a flange here and a flange here that isn't connected. So we definitely have to consider case 2. Okay? Now let's ask ourselves, do we need to consider any of the others? Do we need to consider case 3? I mean, you tell me. No. This is about welds. Same thing with case 4. That's all welded. What about 5 or 6? And by the way, HSS stands for hollow structural sections. So we're talking about tubes and pipes. So we don't need to consider that. Do we need to consider case 7 or case 8? No. All right, so this is really the only case we have to consider is case 2. Okay? So in order to consider case 2, we need an X bar and we need a connection length. Let's do the connection length first. What is the connection length for this connection going to be?
9 inches.
9 inches. That is 100% correct. It is very easy to say 11 inches because you're going to consider this 2 inches. That's wrong. Center of bolt to center of bolt is 9 inches. Okay. Now, what about the connection eccentricity? What is the connection eccentricity going to be for this member? Remember, we are looking at a C10 by 30. So I want somebody to tell me what is the connection eccentricity for this C10 by 30. I want somebody to tell me. Say again? 0.649. Do I have a second on that? So first off, what dimension we're going to look up? We are going to look up X bar. And you're getting 0.649. What table did you find that in?
1-5.
What page?
1-39.
Okay. Anybody else find that? I want to make sure everybody can see that. So we're in table 1-5. So I like to bookmark the C-shaped table. That's just me. I bookmark W's, C's, L's, and WT's. That's what I bookmark. I don't bookmark all of them. Is everybody able to find the 0.649? What's that? Okay. Everybody good? All right. So with these, I can say that since I only have one shear lag factor, I'll say that U equals U2, which is 1 minus X bar over L, which is 1 minus 0.649 divided by 9 inches. So U is what? We'll say 3 decimal places for this. You don't need to go any further than that. 0.928. Do I have a second on that? Because everybody brought their Casio FX115ES plus or similar scientific calculator to class, right? Everybody did.
Yes.
Okay, there we go. All right, so that's our answer. Okay. Sound good? Okay. Now, I want to go to this question here. So, does the channel meet suggested slenderness limits if it is 15 feet long? So, let's look at that. So, slenderness limits. All right. So, we know that the length of the member is 15 feet. Now, whenever you're doing slenderness, take that length and automatically convert it to inches. So 15 feet is how many inches? 180. Now, we also need a minimum radius of gyration. So you tell me, for a channel, is that Rx or is that Ry? Ry. And how much is it? Anybody have a value on it? 0.668. Is everybody able to find that? Okay. So with that, I'll move this up a little bit. What is that? So we'll say 269. We'll just say 0.5. Is that good? Or is that, did I have a second on that? Anybody else? So that, I mean, the number looks right. Now, but here's the question. Does this member meet suggested slenderness limits? It's under 300. So the way that we usually do that, the way that we write that is we'll say therefore okay. Okay? So we'll usually put either okay or NG for no good, okay, or not good. So whenever you see, if you ever see me write like a therefore okay, that's what that means. And I'm writing that because L over R is less than 300. Okay. Does that make sense? All right, any questions on that?
How do you know which axis to use again?
Whichever one has the smallest R value. So if you look at the channel, the C10 by 30, Rx is about 3.43, but Ry is 0.668. So it's going to be more slender that way. So a way of thinking about it is, imagine if you just like wrapped a string around this and lifted it. It's going to be more flimsy that way, so it's probably going to bow more that way than it is this way. So you're trying to figure out which way it's flimsier. So it's like imagine going into Home Depot and picking up a 2x4. One way you pick it up, it's pretty stiff. The other way, it's going to kind of want to flop. That's kind of what this is saying. Does that make sense? Okay. Now, we don't have a lot of time, but I want to kind of knock this one out pretty quickly because it should be pretty easy. Let's look at this L 8 by 8 by 5/8. Now, we're not going to do slenderness on this. We're just going to do shear lag. So let's go back to the shear lag table, and let's ask ourselves, how many cases would we need to consider for this? So let me ask you this. Is this a case 1 or a case 2? 2, because this leg is not connected. So it's definitely case 2. Are there any other cases that apply? Do we have to consider case 3? No. What about 4? No, because these are all, case 3 and 4 are welding. What about 5 or 6? Those are tubes and pipes. Case 7? No. What about case 8? Here we go, single and double angles. All right, so let's look at case 8. Now, when we look at case 8, what does it say here on case 8? Let's read case 8 out. It says single and double angles. But what does it say in parentheses? It says, if U is calculated per case 2, the larger value is permitted to be used. So what we're actually going to do is compute case 2 and 8 and take the maximum of these two. So we'll see what happens. Okay. Now with case 2, we're going to need an X bar and we're going to need an L. Now with an angle, sometimes there's confusion as to whether or not you need to look up X bar and Y bar. Fortunately for us, because this is an equal leg angle, they're both going to be the same. Both X bar and Y bar are going to be equal. So X bar and Y bar are actually going to be equal. And since we're running short on time, I'm going to tell you that that quantity is 2.21. Okay? Now, can somebody tell me what the connection length is? Can you look at this and tell me what it's going to be?
10 inches.
Say it again.
10 inches.
10 inches. That is correct. So therefore, U2 is 1 minus x bar over L, which is 1 minus 2.21 over 10. And I'll go ahead and do that one for you. It comes out to 0.779. Okay. But what I'm most interested in is your ability to interpret case 8, because I know we're running out of time. So we'll do case 8 and then that's it. So case 8, so it says right here, with 4 or more fasteners in the direction of loading or 3 fasteners per line. Do we have 4 fasteners per line or 3 per line? And the line is in the direction of loading. How many we have per line? 3. So we have 3 in this line and 3 in this line. So U8 is going to be what? U8 is going to be 0.6. And we'll say 3 fasteners per line. So with these 2 U values, which one do we use? Now hold on. What does case 8 say? You choose the, what's that? The larger one. Remember, these are empirical. And there you go. Boom. That's it. Okay? That's it. Any questions? All right, don't worry. We're going to have a big old example practicing all of this on Wednesday. But that's all I have, everybody. I'm going to pull the code up one more time, but I will see you all on Wednesday.